So, participation. So we're looking for sort of some active participation in class and labs. First lab, you just come in, but in subsequent labs, you kind of want a little bit of advanced preparation as you come in and present things. And then non-closely supervised work is only worth 25%. And these are requirements of the department and the faculty, really, that a certain percentage has to be closely supervised, and the lesser percentage is not closely supervised. The exam is worth 35%. I want to say, so the final exam, I also want to say there's bonus marks. Like, I'm generous with bonus marks. So if you do something really cool or really fun, show me something interesting, show a sense of spirit in the labs, do something fun, I'm happy to give bonus marks. So it's very possible to get more than 10 out of 10 on the lab. There's 5 labs and they're each worth 10. And you're, of course, free to put your own projects in. So towards the end, people will do a final project in lieu of, like lab 3 and 4 might morph into a single big final project for some people if you wish, as long as it's course related and we can approve it beforehand. But the labs are 10, they're out of 10, but some people will get 11 out of 10 or 12 out of 10 because you've done something really cool, right? And that's good because you can, I'm not allowed to award a mark that's greater than 100% in the course, so the mark will have to be clipped to 100%. But it does give you a good chance for those who are trying to get into MIT or Stanford or get a job at Google or Apple or impress your friends or raise some investment capital. I call them the 100%ers. There's some people in the class will get a mark of 100, and that's those are the achievers, I guess. And so the bonus marks helps facilitate getting a really good score. They call it the 100% principle, and that is how to present. I want to talk directly about how to present on Friday. We have our class at 2 p.m. I've been asked by the media to do an interview. I get constant media requests for the interview. I've been on CNN, ABC, NBC. I've been in Wired magazine 5 times, New York Times 3 times, So I've been kind of like in all these media, and so I don't really need any more media exposure. So I might as well give you guys some opportunity if you wish. So I told them to interview me at exactly 3 o'clock on Friday, because then anyone who wants to do a part of the media interview can stay on after the end of class and become part of a media interview. It'll be a good experience. It's really good experience to learn how to present. So come in on Friday, bring anything cool you've built or have a few words to say if you wish, and this will give you an opportunity to say something and learn how to present yourself, because this course will teach you how to present yourself. If you're trying to get into MIT or Stanford or trying to start a company and raise more than 100 million or something like that in investment capital, or you're trying to get a job at Apple or Google or anywhere else, whatever it might be, learning how to present yourself helps a lot, and I can teach you how to present yourself and how to connect with people in these industries. And I have a lot of connections in Silicon Valley. I'm the chair of the Investment Entrepreneurship Forum and all these other things that may help. So if you need help connecting with these groups, let me know, and we'll do that. But anyway, Friday, there's an opportunity right after class, and so learning how to present yourself in the labs, and you'll learn how to present these labs, learning how to maximize your grade is another useful thing, and doing something fun, showing a little bit of spirit is fun. Thursday lab, which is tomorrow, we've got the lab, so I'll show you how to make a simple camera. I explained yesterday how a camera works. Did everybody have a chance to look through this? Anybody not have a chance to look through it? Because I'll have it here at the end of the day too, if anyone wants to just kind of look through it and understand it. I've got various cameras. We're going to build a camera. Tomorrow, that's what the lab will be. We'll be building a camera. And we're going to learn how to make various sorts of imaging and cameras. And so here is I'll start with this one, I guess, because this is a simple box camera that I made out of wood. And there's a pinhole in here. There's a little hole that lets the light in, and then there's a place to put the film or light sensor material on the back. So just handle it carefully as you pass it around. And take a look at how simple a camera is. It's just a box with a hole in front of it. So that will give you an idea. And then there's other cameras, of course, that have the viewfinders and things like that. And so you can look through this one and focus it. And there's a little viewfinder on the top, and you can kind of see how they work. This is a little bit slightly more sophisticated, but still quite simple and primitive, relatively speaking. And so this is an older box camera. I'm just going to open it up here. So this is a box, and there's a roll of film that goes through here, so you can take more than one picture on the same roll. Take a picture, advance to the next, and so you can see this box is slightly more advanced technologically than the simple box camera because it has a mechanism to roll film through it. This one here, I've put a sensor in here in place of the film. So now this is an internet connected version of this camera. So we can take any of these cameras from the last 100 years or older than 100 years and put modern sensing in it and make it into a networked appliance, but it still teaches the fundamental principles of how a camera works. And then this is just the front of the camera, Polaroid camera, and you can see here, there's a lens here, and that lens, you know, if you hold that here, you'll see an image of the lights overhead. Cast on your hand. If you got a piece of white paper or something, you can actually see the image of the lights overhead. Can everybody see that? Can you see that? See how you can see the light fixture above it? So try that. Just try to make an image of the light fixture on that piece of paper and understand how a camera works fundamentally. What is a camera? And so this first lab is going to teach you those fundamentals. What is a camera? And yesterday, and so what is a camera is an interesting theme to start with. And yesterday I talked about the sequential wave and printing machine and reality, because another fundamental question is, what is reality? You know, what is the world that we perceive? A camera grabs us a glimpse of reality. This is a sequential wave and printing machine, for example. I showed you all yesterday how you can see the waveform. I see these electromagnetic radio waves coming here, and so this is sequential wave and printing machine, and if you have a camera you can photograph these waves, and you can certainly see them to the naked eye. Now, a simple question I have is, this is an interesting question that you find, is if I go through some books here, you see, notice how the wave is weaker when I'm going through the books? Can everybody see that? How the wave is, you know, it's stronger when I'm closer here and weaker when I'm further away. And now if I go through the books, it's weaker. And if I go through a brick, here's a brick. You can see it's weaker going through the brick. Can everybody see how it's weaker going through this brick than it is the waveform? Some of the wave is lost in going through this brick. The electromagnetic radio wave is attenuated going through the brick. See this thick piece of brick here, can you see that roughly? So you can see about how much of it makes it through that brick versus how much of it is there without the brick. So now, the simple question, if I put my hand over there, well, I can also look at the table too, and there's a piece of wood here. You can see how much the wood blocks the electromagnetic radio wave. If I put my hand over it, will my hand block more or less than the brick? Or more or less than the wood, or somewhere between the wood and the brick? Any takers? And how about the brick and the wood together? I mean, It's easy enough to, there's the thick piece of wood and the brick. So you can see some of the wave is making it through the brick and the wood all stacked up on top of one another. And I could throw in a couple of textbooks as well. Throw in this nice thick book. And you know, what's really weighs down on my heart is this stack of exams here. If I go through this big stack of exams, you see how many of the radio waves get through the exams. So if I go through my hand, do you think it's going to block more than the exams, or less than the exams, or more than the book, or less than the book, more than the brick, less than the brick, or more or less than all of those stacked on top of one another? Anyone want to guess?
Probably less than all of them, because like even like when you try shining flashlights through our hand, you can see like some sort of through it.
Yeah, light goes right through the hand really easily. Any other takers?
Yeah, same. Or and everything.
Yeah. So let me try it and let's answer the question. I'm going to put my hand over this. Now, how much is the radio waves getting through my hand? Yeah. Why is light goes through my hand? If I put my hand over a light bulb, it'll go through. Yeah.
Because the hand has a lot of fluids which can be capacitive.
Say again.
The hand can be capacitive due to the blood and like fluids flowing.
Yeah, your answer is partly right. The hand has a lot of fluid in it, and that is it capacitance that we're talking about here? Does the hand make a capacitor? You got the right.
Conductor.
Conductance, yes, it's conductive. The liquids are often conductive. I mean, distilled water, perfectly distilled, might sort of not be too conductive, but most water is conductive. And what happens when you put conductors in front of electromagnetic radio waves?
Faraday cage.
Yeah, it's a Faraday cage. So my hand makes a pretty effective Faraday cage. So you know when you're talking on the phone like this, if you talk like this, you know, everybody can hear you. But if you talk like this, nobody can hear you. And so that's kind of just an interesting observation. See, there's my hand, and a little easier to see if I block lights up. But there's my hand here, and nothing. And then there's 1 finger, 2 fingers, 3 fingers, 4 fingers. See, by the time I put all my fingers there, got almost nothing versus quite a bit of waves. Even just 1 or 2 fingers really greatly attenuates the electromagnetic wave propagation because of the conduction. This metal fire extinguisher also stops it completely. Any piece of tin foil or something will even stop it. So there you have an interesting example of reality. What is reality? So in this course, we're going to ground ourselves in reality and really understand what is reality. What is a camera first from a very fundamental principle. So I want to kind of explain briefly what is a camera, and then just going to go on the chalkboard here, so I'll clear off some space here. And we'll say, what is a camera? So we've got the COFM taken care of. By the way, if you go to ece385 or ece516 wearcam.org/ece516/cofm.htm, that document is there. Called the composition of final mark. So now let me just by the way, Thursday, tomorrow, I will set up the darkroom too and do some shots if you guys want to do a picture with this swim or something, a cool profile shot for your Facebook page or something you want a really cool picture. You can I'll do a portrait of you with the swim motor. You can crank that up and do something really cool, make a really cool picture. Show some reality. So what is a camera? I want everybody to fundamentally understand what a camera is, really from the very most simple form. A camera is a dark room, camera obscura. This word means dark, and this word means room. And so a camera is an abbreviation often for the term camera obscura, which means a dark room. And historically, what happened is people would build So painters, people making paintings and pictures, there might be some scene here, you know, there might be some subject matter here, and then they'll build a room, like a tent, a photographic tent or a camera tent, like this, and then they'll make a little hole in here, and then over here, they'll put they typically put like a white wall. So typically what you do is make a tent out of black cloth all the way around here except for one wall in white. So you'd either paint that wall white or hang a white cloth here, and everything else is black, and then there'd be somebody inside here like this with a paintbrush painting whatever they saw right on that white cloth. And that was how paintings used to be made many years ago. And so if you trace these rays of light come down through that hole, and you can see that you're going to get this image of whatever's out there. And whatever is here will be imaged over here. So rays of light travel in straight lines approximately. Do rays of light always travel in straight lines? Yeah, change of medium will cause refraction, for example. So in water, remember the refractive index of water is about 1.33. This is really evident when you have a VR headset with an eyeglass like this and say, hey, you want to do a selfie or an underwater shot? I do that, you'll see in the video from Sunday. I got a bunch of swimmers together to go an underwater shot. And the thing is, you have to know that if you get a bunch of people, they're all in frame, and then when you dunk in water, they're not all in frame anymore, because the refractive index of water is higher than air, and the light, so you got to get back a little bit to get everybody in the shot. So I always say get shoulder to shoulder, get close together, get way back, and then dunk in and get everybody in the shot. So rays bend. What else causes light to bend? There's refraction causes light to bend. The refractive index of water bends the rays of light. Change of medium. What else?
Black holes.
Yeah, that's another possibility. Maybe something more common that you might see in everyday life, like in a camera.
Heat.
Yeah, heat can create like a mirage. That's a change in refractive index of the air, which again is refraction. I'll keep going here, and then the answer may become evident. So the question is, how big should I make this hole? Tell me the advantages and disadvantages of hole size. What happens if I make the hole larger? Yeah?
You get blurry image.
Yeah, the image is less sharp to a certain extent. And when I make the hole smaller, what happens to the image?
Or you get sharper image, but you get less exposure, meaning the image will be darker.
Yeah, up to a point. As you make the hole smaller, the image gets sharper up to a point, because here when the hole is very large, this point here actually makes a large fuzzy blob. And then as you get the hole smaller, it comes closer to a smaller blob, and thus sharper. The price that you pay for a smaller hole, as you rightly point out, is that the image is darker and harder to see, perhaps. So if you're trying to paint this thing, you've got to let your eyes accustom to the dark. But let's suppose I put a photographic film there and I'm prepared to do a long exposure. In the early days of photography, exposures were long, and people used to have what's called a Brady stand. Does everybody know what a Brady stand is? It's like a big heavy cast iron stand that holds somebody's head in position. My daughter made a Brady chair here. So over here, this thing right here. This is a Brady chair for holding the head still for long exposure photography. So if you want to do photography like it was 100 years ago, here's a Brady chair, and you'd sit in this chair and rest your head back on here so that your head's steady, and you could do a long exposure. You might be able to sit still for a while so that the And then, of course, you could use a smaller pinhole and get a sharper image because you could sit still longer and the exposure could be longer. And if it's a still life that's not moving, if you're just taking a picture of a mountain, you could leave that exposure running all day, and then you could use a very small hole. So what happens if you keep making the hole smaller and smaller and make the exposure longer to make up for the small hole? If you make the hole really small and just leave it exposing all day, or even let the exposure be like 3 or 4 days, let it be a week long, leave the film in there for a week, because you can leave camera in there for years. I've done exposures like 5-year long exposure or something. Is it going to be sharper? If that hole is really, really small. What happens if I make an extremely small hole there? What happens to that ray of light when it passes through the hole? Yep.
It starts to diffract.
Yes, you get diffraction. So as the hole gets too small, you get diffraction and the image gets fuzzier again. So there's a certain optimum pinhole size. When the hole's big, it lets in more light, and as you get it smaller, it lets in less light and the image gets sharper to a point. And then if you go too small, it lets in even less light and the image gets even more blurry again. Because at some point there's diffraction, which spreads the light out again. So diffraction is something you have to think about. And so that's what I want you to kind of understand here, is that there's an optimum pinhole size. And so we could calculate the diffraction. You know, you could use simple formulas for diffraction, 1.22 lambda over d or whatever, you know. You look at resolving power of a circular aperture, or just work it through. You know, the far field diffraction pattern is the Fourier transform of the electric field across the aperture. So we know from simple mathematics, in the physical domain, when you make something smaller, in the Fourier domain it spreads out. So we can calculate that and actually work through and calculate what size the optimal hole should be. How big should it be? So we might calculate, oftentimes we make some simple assumptions, like let's assume the eye is most sensitive to green light, around 550 nanometers. And because the optimal hole size is going to be different for red than it will be for blue. So if your subject matter is predominantly blue, you might say, well, I'll make the hole smaller. But if it's primarily red, you might have to make the hole bigger because the red light will diffract. And so you want to know that my holography professor said to me, he said a good way of, I studied under Steve Benton at MIT, and he invented the white light hologram. And he said, red rotates radically is a good way to remember which frequencies of light bend more, because the red diffracts more. Red rotates radically. And so immediately I said to him in the class, that kind of interruption, and I said, you know, unless you're talking about refraction, in which case blue bends best. So I said, and now how could you not get, you might get those confused. So you really want to understand from first principles that lower frequencies diffract more. And so try to think that through and pick something in the middle, like 550 nanometers green, perhaps, where the eye's most sensitive. Calculate for that wavelength what the optimum hole size is, and then you know how to make a hole. And of course, if you're making this hole, you know, you're going to make this hole in a big block of wood like this, or a cardboard, a piece of cardboard. Now what are you going to do? You're going to drill a little hole like this. Does that make sense? Is that going to give me a good picture? What's wrong with just drilling a little hole through a piece of cardboard? Yep.
Light will be stuck.
Say again?
The light will be stuck in the middle.
Yeah, the light will kind of be stuck, like you've got a long tunnel here where the light has to go through. So how can I mitigate that effect? Yep.
Have the hole and then have it widen after the initial.
Yeah, exactly. So you want to have your hole here like this, and then maybe drill your hole here like this so it widens out. That's kind of hard to do, really, to drill a hole in a piece of cardboard that looks like this. So what's an easier way to make a hole than that? Yeah?
Have a thinner material.
Yeah, have a thinner material. So what I do is I'll take my box, which is really made out of cardboard. Now, in the old days, people used to go inside the camera, but nowadays we make cameras smaller. So in the old day, camera obscura was a dark room and you'd almost always be inside the camera. But today we often make cameras smaller and we don't go inside them anymore, and we just put some sensor inside there to report back the image. So now, if I've got my box, it's going to have an outside dimension and an inside dimension. I've kind of exaggerated a little bit, but I've got a box like this, and then I'm going to make a large hole here. Make a really big hole. And then I'm going to put a piece of thin material like foil, tin foil or something over the hole, and punch a little hole in it with a pin, make a little pin prick in there. And then rays of light, of course, will freely come in like this. So that's what you're going to want to do tomorrow, is you're going to want to bring a cardboard box. You could bring more than one if you want, bring a couple of different boxes.
My hall for free cardboard box.
Say again?
My hall.
Oh yeah, my hall. If you're looking for empty cardboard boxes, there's a lot of stuff thrown away at my hall. Obviously you guys all know how to go to a grocery store, get a cardboard box, or you find one at home, or you've probably got boxes at home that you're not using anymore. You go to a grocery store and ask for some. But you can also go to my hall and get some empty cardboard boxes. The My Hall Center in the basement, there's a lot of them around. You'll find some cardboard boxes, and then you'll bring a couple of different boxes, especially if you can find some box that fits inside the other, then it's easy to carry. What I'll do is stack boxes one inside the other so they don't take up too much space. And then bring some scissors, tape, black cardboard, white paper, and that sort of thing, and maybe some tin foil. So try to think it through in your head how you're going to make this camera, and I'll show you, well, the TAs, the three of us will be here to help you tomorrow at noon, how to build and make a camera. And so we'll basically cut a hole in the box, make a hole, we'll put something over it like this, and then you want to line it with black paper, or ideally if you can find a black box, that's even better, one that's made out of black cardboard, that would be the best. But in any case, you can line it with black cardboard or black paper, and then put white paper on the far side here. So you'll have a box that's largely black except white on the far side. And then what we're going to do to observe this, because we want to observe what's on the screen here, we'll make a second hole here to look in. And that way you can look in and see what's formed the image. And you could even put a small camera phone or something here looking in there to photograph the image that's appearing inside that camera. So we'll show you how to make a camera and how to make a viewing opening to look in and see the resulting image. So that's kind of what we want to do. Now, the other thing to think about, if you want to go a little more advanced, and in this class there's always the opportunity to do fun things that are more advanced. You can try putting a lens or a magnifying glass in this box. What will that do? So now a lens will allow you to focus the image. So that point here, it's a great big opening like this, but it converges the rays to a point again. So now the image will be sharp and clear, but the hole will be really big. Now it's only sharp and clear for something that's in focus, because of course once you have a lens on the camera, you have to focus it. With a pinhole camera, everything's in focus. It's like my pinhole Aramac on my eyeglass. The Aramac is camera spelled backwards, and Aramac is the opposite of the camera that forms the image in the eye, and when you use a laser eye tap, everything's in focus from 0 to infinity. Pinhole, like a pinhole, the opposite of camera, it's almost like a display mechanism. That's pinhole is infinite depth of focus. But a camera here has focus, and that's what this slide rail does here. It focuses the camera. And so you can see, you'll understand that the camera's in focus, and then this is level. There's a little level hanging here to keep this level. And then you can raise and lower the front like this to look up or look down. You see, this is in the old days, cameras had lots of controls on them to make everything quite nice. So you'd level this camera up, so the image would be nice and level, and then if you wanted to look up a building, if you're shooting up, you would just run the front of the camera up and leave the camera level, you see. And so cameras used to have these flexible bellows on them that allow you to adjust. And so that's another improvement is in photography is now you've got this flexible mechanism like this that allows you to not only focus it, because now you can squeeze the bellows in or stretch them out, but also adjust it. If you want to look up a tall building, you'd simply put the back of the camera way down here and the front of the camera way up here like this. And now I can look up the building. And what advantage does that give me? Seems we've forgotten a lot of these historical things of photography. But what does that do for you when you look up a building that way, rather than just point the camera up? What's the difference between this and this if I just point the camera up the building? The camera's looking up at a tall building. What's going to be the difference in the pictures there? Well, let's consider a subject matter that's just a periodic structure. Like, suppose the subject matter is a cos wave or a sine wave, or even just a series of points, of uniformly spaced points. It's a periodic structure, as many urban environments like buildings have various floors. Each floor of the building there's windows that are all about the same size. And so you'll see in this image plane here, there's an image plane here, and there's a center of projection. Now, mathematically, I don't need to draw the whole box. I can just assume it exists, and I can just connect each of these. This one goes here, this one goes here, this one goes here, this one goes here, and so on. Each of these goes through a point. Now, what do you notice about these points here in relation to those points over there? So in the domain, this is a mapping from this domain here to the range over here. In the domain, I've got a sequence of uniformly spaced points. You could think of a Fourier series, various cosines and sines in the domain that represent whatever that is. In the range, you've got some mapping of that. What do you notice about the relation? Now let's consider over here. Here's the domain, and then I'll put a point here, and then in the range, I've got this line here, and I'm going to start taking points and map them. 1, 2, 3, 4, 5, 6, 7, just a whole bunch of points here, and I'm going to start mapping them. Maybe like this. The next one is like this. The next one is like this. And so they're just straight lines. I'll extend that a little bit. And then this is so what do we notice about the domain versus the range here versus over here? Yeah?
Like, it looks like the parallel lines that we see are actually converging when you look at it through a camera.
Actually, there's no real, I haven't done it, it's only in one dimension, so there's no parallel lines here really yet. But that would be true, yep.
Would it be the depth perception of the image? Because it looks more elongated than it
Yeah. It could, well, there could be depth perception, but what?
Yeah, like
The spacing, you hit it right on the head. That's exactly what it is. It's the spacing between the points. You see, in the domain, the points are uniformly spaced here. And in the range, the points are uniformly spaced as well. Perhaps differently spaced, you know, if this point was over here versus way out here. they might be closer together or further apart. There's a scale factor, but the point, uniformly spaced points in the domain map to uniformly spaced points in the range right here. In this case, I've got uniformly spaced points like the floors of a building, first floor, second floor, third floor, fifth floor, and a row of uniformly spaced windows. But in the range, they're not uniformly spaced. They're changing. So the spatial frequency is constant here. It's like in time we're used to the idea of temporal frequency. And what do we say when the frequency is changing? What's that called? Yeah? Modulates is one word. In everyday life, though, what do you say of frequencies that change? Like, if a frequency is changing with respect to time, you know, like,
Chirp.
it's chirp. It's called chirp. That's what people in everyday life, you know, my parents would say the birds are chirping. You know, when humans play music, it's like a series of notes that each have a certain time and frequency, duration and frequency, but bird song is like, so chirps, those are, so this is, you know, you might have something like this, cos omega t minus kx, say, in general, you know, maybe it's a spatial, space and time. But then here, we're going to have something like, you might have something of the form like cos of ax plus b over cx plus d, let's say. And so this is an affine transformation A and B, and then the C is the chirpiness. C is chirp. You know, there's a mathematical transformation going on there, and you can look more into that. But there's something very interesting called the chirplet transform. So if you want to do a little bit of fun advanced reading ahead, look for chirplet transform. Chirplet transform. And it's the world's first transform that has machine learning built right into the transform. Neural network built right into the transform. So there's a lot of work been done on chirplet transform, like for chirplet-based brainwave signal analysis for human brain-computer interfaces based on chirps. And then over here we've got like Fourier transform and wavelet transform. Everybody here know what wavelet transform is? Anybody here heard of it before? Anybody here heard of Fourier transform? Raise your hand if you're familiar with Fourier transform. Raise your hand if you're familiar with wavelet transform. So a wave, does everybody know what a wave is? So a wave is like you can have a cosine wave or a sine wave go from minus infinity to infinity. A wavelet, what does let mean? It's like a diminutive term, right? Wavelet. Like a cigarette is a small cigar, right? So a wavelet is a small wave, right? Yep. It's part of a wave. A wavelet is a piece of a wave. So light, for example, is neither a wave nor a particle. It's a wavelet. A photon is like a wavelet. It's not totally a wave that goes from minus infinity to infinity, and it's not totally a particle. It's kind of in between. It's sort of somewhere between the physical domain and the Fourier domain. So it's like a piece of a wave, and that's called a wavelet. And so the wavelet transform looks at pieces of waves, windowed waves, or localized waves, localized in time and frequency, or localized in space and spatial frequency. And chirplets are pieces of chirps. Everyone knows what a chirp is. Like, you know, sine 1 over x is a good example of a chirp. Frequency gets higher and increases without bound towards the origin, then goes back down again. So sine 1 over x is a chirp. And a chirplet is a piece of a chirp, a portion of a chirp. And the chirplet transform is based on pieces of chirps. And because of the projective nature of cameras, because cameras obey algebraic projective geometry, it makes mathematical sense to look at chirplets when you're looking at images. So if you do Fourier analysis of images, it doesn't make sense because cameras are not always lined up. In the old days, it might have made sense. In the old days, people used to be very carefully level up the camera. And if you look at old photographs of a building, all the windows are the same size in a picture of a building. Professionally done. But nowadays, people just grab their camera phone and point it up at a building like this, and the windows near the bottom are bigger in the picture than the windows near the top, even though in reality they're all the same size, so it's chirping. And so it goes, if I take a picture of this row of lights, it goes from low frequency to high frequency, chirping. And so people just blindly apply Fourier analysis to it when they should really be doing chirplet transform. So that's kind of what I hope you get from the pinhole cameras. You really understand what a camera is fundamentally and what it measures and what it senses, so that you can, at a very introductory level, figure it out. In terms of this course, by the way, you're going to get most of the benefit by taking the course. So if you're looking at this course, if you've been auditing it and you like what you see, please consider looking at your other courses, and is there anything else you can drop, or is there any way that we can get this to count as your technical elective? Because ece516 for undergrads is a legitimate technical elective that will satisfy many of your requirements. So if you are trying to get this course to count somehow, let me know how I can help out. If I can write a letter to your department to make this course count as your AI, whatever it is, or whatever it needs to count as, let me know how I can help, because you'll get the benefit from this course by taking it, because it's lab oriented. I'm going to teach you how to make things, and you get this course. Also, it's a good opportunity to get one of those 100%ers. Like, if you're serious about this course, you can get a 100% grade in the course, and that will help you bring your GPA up. So consider registering in the course, and let me know how I can help. On the way out too, maybe I'll get a group shot of everybody. If everybody wants to come up to the chalkboard, I'll get a group picture of everyone, and then we'll get to know each other. I really want to spend effort and find out what each of you wants to achieve in life and try to help you get there. So let me know, like if you're trying to get into MIT, or you're trying to get into Stanford, or you're trying to, which I can help you with both of those, because MIT is my alma mater. I graduated from MIT, and then I spent a lot of time at Stanford. While I was at MIT, actually, the West Coast was interested in some of my inventions, so I was over there helping get HDR, one of my inventions, high dynamic range imaging, into a lot of the West Coast stuff. So I spent a lot of time. It took me a long time to graduate from MIT, because I spent a lot of time back and forth, East Coast, West Coast, helping companies. So I kind of know that world. I can help you with that, or startups, Silicon Valley, Google, Apple Vision Pro, or Microsoft HoloLens, or whatever. Let me know what you're trying to achieve in life. Yep.
5 minutes.
And yeah, we got 5 minutes left. So, and I can try to help you with that. I can try to help you get something. So I want to spend a little bit of time getting to know each of you, help you get into the course, and also just how to make things in general. Your first lab is going to be tomorrow. You built a camera. Second lab is 1-pixel sensor for a camera. How to build a 1-pixel sensor. That's so easy, but yet I want you to think deeply about it. And then the next lab, we're going to start to get into things like AI and self-driving cars and vehicles. And so what I want to do is I want to make a very simple motor-based fun thing. So we're putting together a lab kit, and we want to give you the fundamentals that you'll need to make a self-driving micro-mobility aid. We're trying to make the Freacle, which is a device that can take you on water, land, or air. So that's kind of, we're building some prototypes, but we want to kind of bring you into this world. My dream is like a mobility aid that can drive down to the water, go across the water to the airport, take off on the runway, fly around a little bit, you know. And so I'm kind of envisioning this thing, I call it the Freacle, the vehicle of freedom of mobility, that works as a micro-mobility solution. That's a self-driving car that can go fetch me groceries. Her name is Nessie. I would say, hey Nessie, go get me some groceries, and Nessie will go and get me the groceries and bring them back here. Or I can ride Nessie down to the beach and go into the water and go across the water to the airport, take off on the runway, fly around a little bit, you know, and that sort of thing. So the idea is the vehicle works on land, in water, air, and also as a vehicle of freedom, it's allowed in buildings, it can enter buildings, and it can go on the sidewalk or on the bike path or on the road. So regulatory issues and so on are coming into it. So that's like the labs 3 and 4 and 5 are starting to ask questions about machine learning to help humanity and other species as well, to help society more generally, and sustainability. So at the intersection of sustainability, technology, and society, sustainable technology, society. So I want to get a group shot. I want to take the last couple of minutes of the class. We've got 2 minutes left, and get everybody up at the front here. We'll get a group shot of everybody at the board here, and try to get to know each other, put a name to a face, and